All right, hello, grade 12 students, IB Chemistry, standard level and higher level. Now today's lesson, right, will be about the reactions of alkenes in organic chemistry. So bear with me, this is now we're getting, even though it's standard level, it's gonna be a little bit tricky. This and alcohols and halogenalkanes are not as straightforward, should we say. There's quite a few things that you have to remember here, right? So I'll warn you up front that it's going to be a lot of stuff all to cover at once. All right, so let's begin. Right, so for those of you, by the way, who are actually Western, because I celebrated this when I was in Chicago. So yeah, happy late St. Patrick's Day. That was March 17th. For those of you who do celebrate St. Patrick's Day, in Chicago was my hometown in America. And yeah, we did actually have really green water thanks to this fluorescing in the water that they did. I don't know if that was really a pollutant. That's probably not a good idea, but that's what happened in Chicago. Right, so beginning with alkenes. Okay? So alkenes have the general formula of CnH2n, and as you already know, it has a double bond, at least one double bond in the structure. This formula, by the way, is similar to cycloalkanes that you see with the cyclic rings for the alkanes. Okay? Anyways, this alkenes belongs to the homogeneous series of alkenes, right? So, and now we know that we have a double bond. You know that each carbon atom in a carbon double bond is sp2 hybridization. Now this stuff, don't worry about it, SL students. You look at it probably later in HL. But if you remember when we did sp, sp2, sp3, don't forget about your hybridization that you've seen there before. Okay? And so basically the double bond, okay, obviously has both sigma and pi bond. And the sigma bond, okay, it comes from a head-on overlap of sp2 orbitals. Okay? That's the sigma bond. And the pi bond comes from the side-on overlap of the p orbitals, like here. Okay? And then voila, there's your pi bond there. I'll show you a more fully 3D animated PowerPoint in just a bit. Okay? But what you need to know from this, okay, for your alkenes is that your sigma bond is stronger than a pi bond. Okay? This carbon-carbon bond, by the way, okay, this double bond is an electron-rich site. Okay, so I hope that you sort of understand that by now for double bonds. Rotating a double bond requires breaking that pi bond. Okay, and there's no free rotation at room temperature. I'm going to look into this a little bit more when we see the 3D animation. Okay, so now let's go to the 3D animation and understand the nature of the so-called pi bond a little bit more, the double bond. Okay, so looking at the alkenes carbon-carbon double bond. So the carbon-carbon double bond in an alkene, you know, has the two different types of bond, which are the result of the overlap of the atomic orbitals like we just saw. Okay, and so the first type of bond results from the end-to-end overlap of orbitals as occurs in a single carbon-carbon bond, the sigma bond. Okay, so the sigma bond is the strongest type of covalent bond. Okay, so the second bond, again, the sideways overlap of the atomic orbitals above and below the sigma bond. That is your pi bond. Okay, and its electron density is less than that of a sigma bond. Okay, now the pi bond prevents rotation about the double bond, and meaning all the atoms lie in the same plane. The shape of as seen is planar, with the bonds around each carbon at an angle of 120 degrees to each other. And you saw that already when we looked at benzene, you remember? And now we're going to get into the addition of things. So we're starting to look now at the reactions of alkenes. Give me a sec. I had to share the screen. Yikes, I'm always stuck on these things. Okay, give me a second. Technical difficulties. Okay, you can kind of see this, but let's go back to here. Addition of reactions. So what can we do with the double bond? Okay. Right. Here we go. This is another way to draw your alkenes. Okay. So what we're going to be looking at first in the different types of reactions for alkenes is what we call addition reactions, right? You really saw a little bit of that last time. Now we're doing it for in much greater detail, okay? A lot greater depth with the alkenes. So, okay, let's talk about the alkenes are more reactive than alkanes, right? That we saw in our last video, because the bond enthalpy of the pi bond is significantly lower than the bond enthalpy of carbon-carbon single bonds and double bonds, okay? So the double bond of an alkene is an area of high electron density, okay? And therefore an area of a lot of negative charge. The negative charge of the double bond may be attacked by electron deficient species, things that are desperate for electrons, that can accept a lone pair of electrons, okay? And those species have either a full positive charge or slight positive charge on one or more of the atoms. So those so-called species are called electrophiles or electron lovers, okay? And alkenes do go through addition reactions when they're attacked by these electrophile species. That is called an electrophilic addition reaction. Okay, so in this first stage of electrophilic addition, okay, the positive charge on the electrophile is attracted to the electron density in the double bond. Okay, so this is here like an electrophile, and it will be attracted to the electron density in this double bond of your alkene. As the electrophile approaches the double bond, so electrons in this AB bond are repelled towards the B side. Okay, then the pi bond breaks and A bonds, in this AB, A bonds to the carbon, and it forms what we call, this is the first time you've seen this word. They don't describe it very well in IB chemistry, but it helps for you to refer to this because A-level chemistry and AP chemistry refers to this when understanding addition reactions with alkenes. But it's good for IB chemistry to understand what this word means too. Because later on when we see these kind of reactions, like I think for higher level it's more important, but sometimes the product that you get, you know, you wonder why you pick a certain arrangement of where you attach it to your structure. And we have to refer to this carbocation, okay? So that's basically a carbon that ends up having a positive charge. That's called carbocation. It's really for carbon, but instead of just a normal carbon, it's a carbon with a positive charge. So anyway, it's an ion with a positively charged carbon atom. And the two electrons in the AB bond move to B, okay, right here, and it creates a B minus ion. Okay, now the second stage of the electrophilic addition, the B minus ion now acts as a nucleophile, okay? So, and then attacks the cation. I can't even pronounce it, cation, yeah, cation. I don't know why to do it that way. Cation, carbo-cation. It's kind of a tongue twister. All right. The lone pair of electrons on the B minus ion are attracted towards the positively charged carbon in the carbocation, and then B will, of course, bond to that carbon, okay? So both electrons in the bond that joins the B, okay, to the carbocation come from the B, okay? So that's like a coordinate bond, right? You could have technically drawn an arrow from B to C, since the B was the one that was really donating the electrons to that carbon. Yeah? Now, before I get to hydrogenation, let me go back a little bit, because you need to remember, I need you to see what a nucleophile is, because they had just mentioned that word to you. Okay, so let's just review this first, because this is important for you to understand what this is. Okay, I hope you can see that. Okay, so you already have an idea what an electrophile is, electron lover, okay? And 6 electrons, okay, in reaction. So we saw that earlier in the other animation for what on earth is an electrophile. Things that are deficient with electrons, okay, and then they're really looking for electrons. Now, the word we just saw, nucleophile, okay, means nucleus lover, okay? So it's rich in electrons, usually negative charge anions. And so they try to donate electrons to an electrophile in the reactions and forming bonds. Okay? And then here again is our carbon-carbon double bond in the alkene. Okay? So again, the pi bond is electron rich, and it acts as a nucleophile, and it attracts electrophiles to form bonds with this structure. Okay? Now you understand the difference between electrophile and nucleophile. Okay? Back to the animation. Okay, now we are looking at another type of, well, okay, let me go back here. I don't want to go quite into this one yet. Let's go back and review that first addition reaction a little bit in more detail. Okay, so let's look at this one, right? Okay, now that you know the double bond is an electron-rich site that can undergo addition reactions, okay? Let's get the general structure of this equation first. Like, how do we express this first type of addition reaction, okay? So here, okay, in this one, in this addition reaction, right? So 2 molecules, right, add together to form one larger molecule, right? And then we say that the incoming molecule will add across that double bond, right? Broke that double bond, and then we got now just single bonds everywhere. So that's the general structure of it, okay? And then so I just want you to be familiar with this. Sometimes you would see it like this too, okay? Sometimes you see it looking like this. You can also see it looking like this, okay? This is another way to express that. Actually, no, let me show you. This bit of picture here. Oh no, that's the same one, man. Yeah, this might be a little bit better. Kind of. Yeah, same thing. I have to have it look different. This is more general. Here we go. This is a little more general, like, way to express this first addition reaction, okay? So that AB could either be here too or down here, okay? Because the other one you saw, it looks like this, where you have the AB either on this side or that side, okay? One way or another, it broke. Just mind you with this one, okay? Pay attention carefully that, you know, you're using a nickel usually as a catalyst here. So that's usually the general way that this first addition reaction happens, okay? So we have an alkane, ethene, remember ethene the name, okay? So it's reacting with a compound, arbitrary compound, it could be any elements. I just call them XY. And here's your nickel catalyst, okay? And of course, the double bond will allow the X and Y to be on, well, the X on one side and Y on the other side of the molecule, okay? And again, the way we describe this, okay, is so we say that it's added across the double bond, right, of this alkene. Got it? Alrighty, now we will go into, okay, the hydrogenation of alkenes. So what this is we are basically going to, okay, when we hydrogenate an alkene, right? This is another addition reaction, by the way, just so you know. Okay, this is another addition reaction. So when we do this, we are adding hydrogen to this alkene, like here. Okay. So we add a hydrogen to it with the presence of another nickel catalyst. Okay. So what will happen here is a double bond will break and an extra hydrogen will add to each end of the double bond. This is a condensed formula, so we'll show it in detail in the animation what it looks like, okay? Again, the hydrogen, extra hydrogen will add to each side of the double bond, and then we will go from an alkene, of course, to single bond alkanes again, okay? So yeah, so this one, yeah, this one is kind of a semi-structural formula, so that might be a little bit hard to understand until you see the animation. Got it? Yeah, this one also, if you rewrite it like that, as instead of a condensed formula, you write it out like that. Here's a double bond, and then here's your CH3, 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 okay? So it's a little bit different. Now, okay, so let's look at the animation of how this works. Hydrogenation, okay, so here we go. That's the general formula that we just saw, okay? And then, oh, by the way, just as a sidetrack, you know, vegetable oils are unsaturated and may be hydrogenated to make margarine, okay? So yeah, and that has a higher melting point. In case you want to see the application of this in real life, why do we care about hydrogenation? Okay? Now, here's some specific stuff, okay? For this particular process, besides from using nickel, we usually have a temperature of 200 degrees Celsius and a pressure of 1,000 kilopascals. Yeah. All right. Oh, I didn't have the whole animation here. I wanted to show you. God, I hate when that happens. Well, okay, I'll do it a little bit later. Yeah, I'll write it out for you when I get to the whiteboard. Let's see. Now, after hydrogenation, let's go back. Sorry. Well, okay. I mean, I can describe it again. I think I might have lost a slide. Sorry, I should be doing it on the whiteboard, but okay, whatever. Okay, back to hydrogenation. Yeah. Basically, okay, what's happening here, okay? The bond will break and a hydrogen will be inserted, okay, on each side of the double bond. Okay, so it would just add to the double bond. You can write this out on your own, by the way. I think you guys can do that on your own, okay? So what you get is an alkane, right? And then this is, so one branch is coming off, like, let's say the second carbon. And then, you know, we have a molecule like this one here. Is what we form is an alkane molecule now, and it's called methylbutane. Yeah. So anyway, and we don't need a number in front of this. We don't need like 1 dash or 2 dash, okay? Because the methyl group can only be on either side of the second carbon, okay? So there's no need to have a number here. It just becomes methylbutane. Hope that makes sense. That's butane. Okay, that is for hydrogenation. So then the next thing to do would be the next thing on our list. Okay, here we go. The next thing we do is reacting a halogen, okay, with an alkene. Okay, so now here is another addition reaction, again, for the alkene. So, okay, the atoms of the halogen will add across the double bond, okay? Okay, so yeah, the alkane that results is another alkane that we get again. And this is going to be a di-substituted saturated alkane. Remember, alkanes are always saturated, alkenes with a double bond are unsaturated, okay? But anyway, what I mean by di-substituted, it's like, you know, the halogen bromine is put at two different places twice, okay? So it's a di-substituted saturated alkane that you get as a result in this third type of addition reaction. I'll call this 1-2-dibromoethane, okay? So anyway, this type of reaction is useful, like as you see, this is something that you do in an experiment, okay? But it's a test for what is known as, we call the unsaturation test. So basically, like as seen here, or pretty much anything with a double bond, okay? It decolorizes, okay? So I hope you know what that word means. Not colonize, that's spelled wrong. Decolorizes, okay? It decolorizes bromine. Usually the bromine is not going to be pure bromine because it's a little dangerous to deal with in pure form, but we can still deal with bromine water, which is still having natural red-brown color that normal bromine would have in pure state. But anyhow, so the alkene will react with the bromine, okay? And then it will produce a colorless solution. Okay, so let's look at the diagram here on the right in these test tubes, okay? So if you look at these, okay, I'm looking at the first one, the first test tube on the left. This is using sunflower oil with bromine water. So obviously you can tell here, it's clear. So that means that the sunflower oil is reacting, right? It's reacting with the brown, red, or sorry, the bromine's red-brown color, and it breaks the double bond in this reaction, okay? And then you get, in the end, a colorless compound, okay? Second test tube, this is coconut oil with bromine water. This one, however, it's still brown-red, I guess. So if it's still brown and red, even after we add coconut oil, so that means that it must be a saturated hydrocarbon alkane to begin with, because it's not reacting with, you know, the coconut oil. The coconut oil is not reacting with this bromine, right? So it's just simply dissolving. So that means that then this was originally, it's a bromine with some alkane, okay, instead of an alkene. And then the last test tube on the right, the peanut oil with bromine water. So again, it has gone clear, just like the first test tube, this peanut oil with bromine water, which means that the peanut oil must be an unsaturated, okay, hydrocarbon, such as an alkene, since the bromine is reacting with a double bond to form this colorless compound. Okay, so again, basically what comes out of this test, to test for the unsaturation, we basically add bromine water, right, which already has bromine, pure bromine liquid in it, and then that can react with the double bond, got it, in your alkene, and it produces a colorless compound, and then, okay, then, you know, it becomes a saturated compound like your normal alkane is, and hence the red-brown color will remain for the alkane, okay? So now let's see if we can look at some pictures of this a little bit better. Not that one. Yeah, I think this picture will be a little bit better. Okay, so again, that's not as red as I hope it would be for the bromine water. One is clear, one is not. Okay, so again, a few drops of bromine water are added to the test liquid and shaken. If a carbon-carbon double bond is present, the bromine adds across it and the solution turns colorless. So this is the one that proves we have the alkene, and this one proves that we probably had an alkane. Okay? Hopefully that makes sense. So, okay. Oh, God, the arrow sign is missing. This is the general equation in case you guys write it down, okay? This is the way it is. This is your acene, bromine, closing water. So this is together, bromine and H2O is bromine water, okay? And then arrow, that should be an arrow. And then you have now your alkane, and then still with water as well. Okay, but because water is present in such a large amount, okay, a water molecule that has a lone pair can add to one of the carbon atoms, okay, and then followed by the loss of a hydrogen ion. So this could happen as well. This one and then arrow, and then you get this one, and then you end up having like an OH attached instead from the water because there's so much water to begin with, and then you end up forming like an acid here, okay? That is very possible as well. So, but, okay, the major product, okay, of this test usually is this 1,2-dibromoethane, okay? No, sorry, 2-bromoethane 1O. Okay, so this is the main product instead of this one. So it's more common to have the alcohol version than you do the one with the bromine attached. Okay, so there's a favorite product in this reaction. Okay. Now let's look at this again. Okay, so let's look at the reaction with bromine. Here we go. Okay, alkene reacting with bromine to form the bromoalkane by electrophilic addition, which we just saw. Okay, so the bromine molecule has no permanent polarity. Okay, but as it nears the alkene, the electron density in the Br-Br bond is repelled towards the bromine atom that's furthest away from the alkene. Okay, so then there's a temporary dipole. Now, the electron density in the double bond in acene attacks the slight positive charge of the closer bromine, so that acts as an electrophile. So then this causes the bromine molecule to split, okay, by heterolytic fission, okay, and then a bond forms between one of the carbon atoms and the closest bromine atom, and then that forms, of course, a carbocation again, and then you now have a single bromine negative ion, okay? Now the lone pair on that bromine attacks that carbocation, and it bonds to the other carbon atom, okay, and forms now 1,2-dibromoethane, which we saw earlier. Okay, so let's look at this reaction with, or we'll go to this one, HBr, a little bit later. Yeah, we'll get to that. We'll come back to it. Okay. Right, okay, I think you're good now for the bromine test, okay? All right, so here is similar thing, but then here we're doing it with chlorine, okay, instead of with bromine, all right? So your prompt says, state the products of the, okay, reaction of but1-ene and but2-ene with Cl, with chlorine. Okay. So here is your structure that you started off with, the alkene. Here is your chlorine, your pure chlorine. Okay. So basically what's happening here, okay, what we got going on? Basically, it's chlorination. This is what we call chlorination process. when you were adding bromine is bromination. Yeah. So this is chlorination addition reaction. Okay. So then, you know, this is chlorination where the Cl2 here, okay, will break this double bond, okay, between the first and second carbons, and then we'll add a Cl, okay, to each side of that double bond where it used to be. Yeah. Hence, this is how we got this first one. Then we call that then 1,2 dichloro, okay, butane. Okay, butane, A and E. And now this one, in the second one, okay, so again, slightly different. Same type of reaction as before, in addition reaction, okay, because we're still breaking a double bond, right? And the chlorine, again, is added across the double bond. The only difference is from the first one, the only difference is that this time the location of these two chlorines is going to be different, right? It's going to be placed on a different part. Not number 1, number 2, but now number 2, number 3. Right? So yeah, now the chlorine will be on position 2 and 3. So basically, this is like an isomer of this first reaction above, okay? Though it is a different compound because now we call this 2,3 dichlorobutane. And yeah, and it doesn't really matter, by the way, where I put the Cl, okay? They could have both been Cl here and Cl here. It could be on the same side, but that gets into cis and trans, but we're not gonna worry about that, okay? So yeah, so I could put the Cl on either side, okay, or a different side. For SL standard level, it doesn't really matter, okay? You could just do either way, as long as they're both on number 2 and number 3. Make sense? Okay, so that's how you do a little chlorination instead of bromination. Okay, now we're getting into adding a hydrogen. Okay, so what we did earlier, we was adding an alkene. So when we're doing the addition of the alkene with the hydrogen halide, okay. So this is basically an easy way, you guys, to make a halogenolkane. Okay, this is like a halogenolkane. And we will look at this reaction a lot in greater detail after we finish with alcohols, okay? So after we look at alcohol reaction, we'll come back to these kind of compounds in their own type of reaction, okay? So, okay, now when we do this, here we have an alkene again, okay? So, and then we have a double bond and we add the HCl, the hydrogen this is a hydrogen halide, just in case you want to call that. HBr, HCl, whatever, HI, anything with H next to a halogen from group 7 is called hydrogen halide. You should know the word halide by now, okay? Now, the problem with this though, when we do this, okay, when we do this addition reaction, let's say on a larger unsymmetrical alkene, this happens to be symmetrical, so this comes out pretty straightforward and how that H goes to one side and the Cl goes to another side. Make sense? But the problem is sometimes when you have a larger unsymmetrical alkene, we can get more than one product, okay? As you can see, like what happened here, right? So in topic 20 for higher level students, you guys, so we'll understand more in very painful details, by the way, more of which of these products will be the best correct product. Okay, that will be in topic 20 for HL students. But for everyone, SL, HL, for now, for topic 10, all you need to know is that when this happens, when you add a hydrogen as a hydrogen halide to an unsymmetrical alkene like this one, just know that you will usually get 2 possible different products. And then they want you to be able to estimate and draw them out what they would be, okay? So with this addition reaction of but1-ene and hydrogen chloride, okay? So here's your structure, okay? So Okay, with the HCl, either the Cl is added to the second carbon and then the hydrogen to the first, or the Cl is added to the first carbon and then the hydrogen is added to the second carbon. So that's what we have here, okay? So in this case, this one, that Cl is added to the second carbon and the hydrogen to the first carbon. In the other possible product, the Cl is added to the first carbon and then the other hydrogen is added to the second carbon. Make sense? That means second carbon over here, yes. So yeah, so that's what happened. And so then they get two names, of course. One is 2-chlorobutane, the other one is 1-chlorobutane, okay? Right? Okay, so that is a typical, reaction of when you add, a hydrogen halide. Now let's see the animation for this in detail. Here we go. Let's look at the hydrogen halide of HBr. Okay, so the alkenes react with hydrogen bromide to form bromoalkanes by electrophilic addition again. So hydrogen bromide is a polar molecule, you see the slight polarity. And so the electron density in a double bond in ethene attacks the slightly positive charge on the hydrogen atom in HBr, which will act as an electrophile. So a bond forms between one of the carbon atoms and the hydrogen atom. So that forms your carbocation, your positive carbon there, and then the Br is left alone as a Br minus ion. Then the lone pair on that Br attacks that same carbocation and then bonds to the other carbon atom, okay, and forms the bromoacane, or this is your bromoalkane. So let's repeat again. Just so you see the first time. Okay. That electron just goes to the Br. This forms the first bond. Yep, then now there's a bond between that carbon and hydrogen. Then Br is an ion, then the Br will attack or most like donate the electrons to that carbon. Okay. Yes, and then forms the polymerization. Okay. Now I haven't really showed you what happens with an acid. Let's look at this. Okay, reaction of alkenes with an acid. Okay, alkenes can be hydrated by reacting with cold concentrated sulfuric acid. Okay, so sulfuric acid is a polar molecule. So the electron density in a double bond, okay, attacks the slightly positive charge on the hydrogen, the first hydrogen. That's the electrophile. Then a bond forms between, okay, the carbon and the hydrogen here. And then we also get the carbocation, right? And then here, this is left with an extra pair of electrons, okay? That is written very badly. It's really HSO4 minus ion that's left over, okay? That broke off from the H2SO4. Make sense? Because we only lost one hydrogen so far of this acid. And that what's left is a HSO4 ion. But we show it this way because the lone pair is on the oxygen, just so you know. Okay? So the lone pair on the oxygen, okay, will attack this carbocation and then it forms that bond there. And then you get now a compound called ethyl hydrogen sulfate. So if ethyl hydrogen sulfate is warmed with water, ethanol is formed, and then you regenerate your sulfuric acid. So it's quite a very useful reaction, actually. You're making back this famous alcohol component for beverages and alcoholic drinks, but you still also retain getting back some of the sulfuric acid that you used, okay? They didn't really cover that in IB, but it's covered in A level in AP, so you might as well know it. Okay, so that is then all you need to know with that. Let's go on to one more type of addition reaction. All right, here we go. Now, sorry, this is where we are going to deal with adding water, okay, to your alkene, all right? So, okay, so we react your alkene, okay, with water to make an alcohol, okay? So in this reaction here, okay, so the double bond is broken, yes, and then water adds across the double bond. Here's your water here. So when this happens, you know, we need some very specific conditions in the industry, in the plant. Those conditions is you either use phosphoric acid as a catalyst, and you use a temperature of 300 degrees Celsius, but a slightly lower pressure than you would expect at only 70 atm for pressure. Okay? So that's some conditions that you need to have when you start this reaction between water and your alkene. Okay, so we got that 300 degrees, 70 atm. Okay, so yeah, so the double bond is breaking with this alcohol. All right, so what will happen then, okay, is that the H2O will break the double bond and we'll have an alcohol because now we have an hydroxy, right, the OH, hydroxy functional group on one of our carbons. And then the other hydrogen that was broken off from H2O will be on another carbon, on some other carbon, okay? Okay, so now again with this one, look at this, okay? Again with this particular reaction, we could have had two possibilities of the molecule if the molecule is bigger, okay? But this one is, luckily for you, it's symmetrical, okay? So we only really have this one possibility, okay? But sometimes I feel like the IB test, even SL, they'll probably give you a bigger one than this, and then you add water to it, and you might have more than one product, okay? But this one happens to be symmetrical. Maybe in your practice problem, you get some that won't come out to be symmetrical, okay? But that's your one possibility. And again, this is your butan 2-ol. You could easily just call this 2-butanol, okay? Remember, I like that name better than having the 2 separated from the OL, okay? So I can easily call this 2-butanol. All right. Okay, that is then addition of water. I don't think I have anything else to share with this one. Okay. Now I will save this for later when we come back to HL. Okay, understand symmetry. So we'll come back to that later. I don't want to bombard you all with that now. Okay, and I think now we are ready for, yeah, okay, we're ready for polymers. Okay, now, let's just talk about what this is first. Hopefully you all had some understanding of what polymers are, okay? How is it not on that slide? Give me a second, you all. That doesn't help me a lot. Zoom is harder to use in Google Drive or Google. Okay, I hope you can see this. Okay, so we're on polymerization. Okay, now let's understand what a polymer is first. Okay, a polymer is a large molecule made by linking together small repeat units called monomers. Monomers are smaller, polymers are bigger. Okay, now if you remember when we did the last video on like some alkanes where we had like chlorine or whatever added to that, and we had the free radicals, right? We had the free radical substitution. So there's a similarity of that to this in this particular mechanism, okay? So you will see some similarity between how there are free radicals created here. So anyways, the monomer is something like smaller, like this, and then it makes up a much bigger chain or like connection of these repeating monomers that will repeat over and over again. Now you're going to start to use notations for polymers in organic chemistry. And I'll explain what this means in a minute, okay? What all this parentheses and the N means when you write the structure of a polymer, okay? So yeah, usually what happens is we end up having, when we have a bigger polymer, we have the word poly in front of everything. Okay, so let's start over again to explain in more detail the mechanism. Okay, so, okay, then pretty much, okay, this is polymers basically, okay, a large covalent molecules, and they contain tens to thousands, right, of atoms, and they're formed by adding together these small molecules, you know, the monomers, okay, and then the entire process is called polymerization. Okay, this is the British spelling. American spelling is with a Z instead of an S. Okay, so don't be confused between those two. They're pretty much the same thing. Okay, so that's what happens here. So now addition of polymerization, or addition polymerization reaction. This is what it is. It's another addition reaction, but it's called polymerization. So it involves molecules with a double bond, okay, your alkenes, smaller alkene units, and then they break apart that double bond, and then it adds to the next monomer, okay? So a monomer will have a carbon-to-carbon double bond. Each single monomer has a carbon-to-carbon double bond, okay? And then the polymer, this is the arrow going and creating a polymer, will have a carbon-to-carbon single bond that's kind of strung along like a big string, okay? Hope that makes sense right there. Now I'll look at this a little bit later. Polymers, okay, obviously very important because they make plastics, everyday plastics. You see these symbols for all kinds of your plastic products and your plastic water bottles and so forth, okay? And this is more about like what can be recycled, because we have plastic is a pollution problem, right? That the world needs to fix, by the way. That goes into a whole different topic here. So I don't want to go into that detail now. Okay, so, okay, now what will happen here, okay? So for this one, let's say, for example, we got then, okay, we got polyethylene here, okay? So formed by, this is polyethylene. It's formed here, and that came from a single ethylene monomer. So this is your polyethylene. Now, these are your single ethylene monomers, the smaller parts of the polymer, okay? And then they created the massive polyethylene, okay? So what would happen is in each ethylene monomers, double bonds, they break, and they will allow it to bond, right, to the next monomer, okay? And then basically just keep doing that, and it gives us a saturated long chain alkane, okay, of carbons and hydrogens. Now, let's explain what the brackets or the parentheses mean, okay? So the parentheses, the brackets, okay, we use them here to indicate that it would keep going on, okay? So, and then the N is for by how many amounts, okay? So that's really what we use for notation here. These are all CHs, CHs, CHs. So this, with this line that cuts through your bracket, it implies that it could have gone longer than this, okay? It could have gone longer than this, and then this would be like for how many repeats, okay? How many amounts. You'll see some examples later how we do this. All right, now another one here is polychloroethylene, or also known as this one, I mean, is polychloroethylene, PVC, polyvinyl chloride, and that's produced from a single chloroethylene monomer. Okay? And again, when this happens, when this polymerization happens, the double bond will break, leaving us with, a single carbon-to-carbon backbone, yeah? And so now look at this carefully in this structure here. So this is your carbon-carbon skeletal backbone, alkane, that we created from this breaking of the double bond. And on every second carbon, we will have the chlorine attached. This one, and then the next second, the next chlorine, and so forth, okay? So on every second carbon is now where we have a chlorine group, the halogen attached. So obviously, this is going to have very different properties to, let's say, something like polyethylene above, okay? So, yeah, because I mean, why? It's got a chlorine group, right? Compared to this one down here has a chlorine group. And so there will be some dipole attractions. Make sense? And that's that will definitely, that's gonna change, okay, for this polymer. So it will just make it very different properties. Okay, so now here, next one. Okay, so here again, how we did this doesn't have a halogen. It's called polypropene, this one. This is a single propene monomer, okay? And again, so this one I'm looking here, this double bond will break again, forming all the alkanes. Okay? But what you want to draw, okay? So is that the carbon-to-carbon double bond that it breaks. So then now the CH3, okay, would be then kind of like a methyl group on the alkane, right? Yeah, so it would be a methyl group now on the branch. So again, the carbon-to-carbon double bond will break, and that will allow us to join these monomers together, okay? But on every second carbon, so this would then, yeah, it's supposed to have another CH3 here. I forgot to draw it in, okay? So then you have another CH3 over here, another methyl group over here on every second carbon. This is the first second, this is the next second, and so on, okay? So we would have one on every second carbon. Now let's see the animation for this, for polymerization. Just a second. Okay, here we go. Let's look at polymerization again and with the full animation. Okay, so now the similarity of what you saw when you were looking at those free radical substitutions that you saw way back at the alkanes. So this reaction, okay, is a free radical chain reaction. It involves a free radical, okay, produced by oxygen initiators. Okay, so the free radical breaks with an ethene molecule, breaks the pi bond. One electron goes to form a bond between one carbon and the free radical. The second electron moves to the other carbon. So the end result is a new free radical right here. Okay, and then a new free radical can react with another ethene molecule to create a longer free radical. This is where, because you don't really see in the textbook how you really start the chain, the repeat of the different units. This goes again, right? So it just repeats itself over and over again for each monomer that keeps getting broken like this and being a free radical that joins back to the rest of the larger polymer, okay? So then these are what we call chain propagation reactions. Okay, and that keeps going on until two free radicals react with each other in a chain termination step, okay? So, and that can occur at any time. So polyethylene, polythene, I mean, has different lengths, okay, in its chain. So for an example, with a question about polymers, we look back at this one. Right, now, okay, this is the question that you usually would get, okay? So basically, okay, so the following, you got a polymer chain, okay? This thing is actually called polystyrene, right? And your question is to identify the monomer, the smaller unit, where it came from. So basically, you're identifying what is your repeating monomer unit where this polymer was produced from, okay? So you need to show what monomer made up that polystyrene. Got it? Now, when you look at something like this, you basically need to try to find, okay, so you need to find where, or look at the repeating pattern, okay? What's the thing in this polymer that just repeats itself over and over again? So you're gonna have to cut this polymer into the repeating units that it's made from, the monomer units that repeats itself. And each monomer unit, as we already know, in polymerization, is gonna have a carbon-carbon double bond, okay, in there, an alkene, right? That just repeats itself over again. So what we need to do here is simply cut this. I'm going to zoom in, make it bigger. So we're zooming in and we're going to cut it at different parts of the polymer where we can recognize the repeating unit. Okay? Repeating, 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 and so on. Okay? So in this case, if you notice, every repeating unit has a phenyl group. Familiar? Your hexagon with a ring in there. That's the shortcut lazy version, right? Or it should be the shortcut of having to draw double bonds for the benzene that you guys are already familiar with, the benzene ring. So that's a shortcut method of the benzene ring, but as a functional group, it's a phenyl group, remember? So then each of these repeating units is your monomer. Does that make sense? So then that means that the monomer is most likely going to be something like this, an alkene, a straightforward ethene, but then you have then basically a phenyl group attached to the alkene. Okay, that's your basic repeating monomer. And this is an arrow up, by the way, to make that polymer polystyrene. I hope that is not too bad for you. That's kind of like the typical question you get about polymerization. Okay. All right, now we can just go back and let's just clean up all our understanding about this alkene reactions that we saw earlier, okay? So I'm gonna clean it up a little bit because there's so many of them that you've seen. So, okay, so basically, right, in these alkene addition reactions, you've seen hydrohalogenation, okay? HX, some kind of compound where the X is a halogen, fluorine, chlorine, bromine, iodine. You've seen your hydration, okay, adding water and usually make an alcohol. And then you see the addition of the halogen directly from diatomic halogens. And then hydrogenation, where you just add a hydrogen across the double bond, okay? So I'll go back and review them a lot more cleanly and very quickly before we end this presentation, because it's already getting a little too long, really long. Oh my God, I'm so sorry. Okay, so again, from the beginning, reactions of alkenes and addition reactions. Why are alkenes more reactive than alkanes again? Okay, so this is because the double bond is very reactive, right? Because the pi bond can be easily eliminated, okay? Right, it can be easily eliminated since it is not as strong as a sigma bond. Okay, so here again, this is ethene with HBr, hydrogen bromide. Okay, so yeah, when we do this, the double bond is going to be eliminated, or should we say broken, and each carbon we'll be able to make one additional bond. Okay? So from HBr, the H can go to one carbon, the Br, okay, can go to another carbon. That's your addition reaction there. And remember, the way you name this one, it doesn't really matter, okay? So if it's one bromoethane, or the way we position this, because look, if I put, let's say, the bromine somewhere else, I put that bromine on this other carbon instead, we end up numbering this from the right side, correct? Instead of the left. So, you know, and it would be the same thing anyways. It would still be one bromoethane. Make sense? Okay, now, remember, there are rules about which side of the double bond gets the hydrogen and which gets the bromine if you were having unsymmetrical alkenes. And that is going to happen when you're going to have, you know, 3 or more carbons, okay, in your alkene. But again, like I said, that's kind of covered in topic 20.1, right? 20.1 in HL chapter. All right, next. So again, more the reactions of the alkenes. You have alkenes with halogens, chlorination, bromination, and so on. Okay? And again, the reason why it's important or useful is because it allows you to tell the difference between alkanes and alkenes. Okay? Then you have the alkenes with the water, right? And that usually forms your, okay, so you add a water across the double bond, right? So one of the carbons will get a hydrogen, and the other one will get the hydroxy group, the OH group, right? And then you make an alcohol. And then remember, it doesn't really matter which way I draw this really, whether OH is here or here, because in this situation, you know, it's still going to be SNO. Okay? You could say ethane 1-O or SNO, but we don't need to because it's the only functional group I got, and it's going to be on the first carbon on one end or the other. Okay, that's in this situation. But of course, bigger ones will be different. Okay, if you have a bigger one, we looked at that when we were naming alcohols in that one section when I taught you how to name alcohols. Okay, and then we have the other addition reaction of adding hydrogen to alkenes called hydrogenation, right? So again, here we add hydrogen across the double bond. We need the nickel catalyst for this process. Sometimes I've seen on your IB test that they use palladium instead of nickel, okay? Anyways, either nickel or palladium, but nickel is the more common one. And then that turns the ethene into an ethane. So basically, you know, this ethene was an unsaturated hydrocarbon, and then it becomes ethane, a saturated hydrocarbon. And yeah, and then like I told you earlier, with hydrogenated oils, right? That's how we make them when we're adding hydrogen across the double bond, right? Sometimes you can add that into a triple bond as well, but we won't look at that for IB Chem. Okay, and then of course, back to polymerization one more time. Here are your monomers here. They're ethene monomers, right? Look how they repeat themselves over and over and over again. You could have drawn like a circle around all of these as the monomers. Again, arrow down, and then you end up making like your big whatever chain of polymer. Okay, so again, this is what happens when an alkene undergoes an addition reaction with itself, okay, to make a bigger polymer. So here are ethene monomers, and they all add together to form a long chain. Now, okay, mind you, this particular picture, excuse me, I think I might have more polymers, or sorry, more carbons than the number I actually had in the original, you know, selection of monomers, but you get the idea, okay? This could go on and on as long as I had enough molecules of ethene, okay? Because when the double bond is eliminated, each carbon can make one more bond on each side, okay, if that makes sense. So I could go on, and the repeating unit, okay, over and over again can be abbreviated more shortly, like with the brackets here. There's a line, the line. So in this case, it's repeating CH2, CH2, right? CH2, CH2, right? That's the repeat monomer that you see. You put that in the brackets, and then you have N here, okay? See how many amounts you have there. And of course, we care about polymers because it makes so many plastic products. okay? Plastic sheets, plastic that, you know, Teflon here is like for kitchenware. You can make bulletproof vests that police use to get, well, not killed when they get shot by bullets, things like that, which I'm very familiar with, by the way, with the polymer vest. Okay, so that is, yeah, pretty quick and easy review of all these reactions with alkenes. And again, here's a typical question that you would have about the bromine model test, right? Two substances in the lab, octane and octene, right? So yeah, you basically, you know, have one beaker that is, you know, no reaction. The other beaker has a color change, but you know that you have one is octane or octene, right? Does that make sense? So yeah, then, so basically it's just like what we saw earlier, okay? So basically you are just going to, you know, decide which of these beakers is going to be the alkene, okay? So obviously the alkanes do not react with the bromine, and then the reddish brown color it starts with will stay the same and not change, and alkenes will react with the bromine. So then the red brown color that the bromine used to be will change and become clear, colorless, and then you know that that originally was an alkene instead of alkane, okay? That should be enough for that one. Stop share this one and then go to the next one. Okay, and then finally going back to a lovely animation. Okay, let's look at some more review for electrophiles. Okay. All right, electrophiles all contain a lone pair of electrons. True or false? Electrophiles are desperate for electrons, so this is false. The carbon-carbon double bond is an alkene. We know that already, we were told earlier. It's an area of high electron density. True, okay, that was defined in the beginning. Electrophilic addition to alkenes proceeds via a carbocation intermediate. Remember, that's your positive carbon atom. True. Bromine water is used for the unsaturation, the comparison of alkane to alkene. True. This question, by the way, you don't know yet. You learn in topic 20.1 for HL, okay? This is what we deal with for number 5 here. When you deal with reactions, addition reaction to the alkene, when the alkene is 3 carbons or larger and unsymmetrical, and then you have to pick which one's the best product, okay? We'll find out what that answer is. I'll come back to it later in topic 20.1. Okay, but that is in a nutshell your review, all right, of the alkene addition reactions. And then the next lesson will be about the reactions of alcohols in organic chemistry. Okay, so that next video will be posted shortly. All right, see you soon.